Hello everyone. We're going to look at learning target 3. Okay. And learning target 3 has to do with nuclear chemistry, the role of protons and neutrons in the nucleus, and how we get certain decays of radioactive isotopes. Okay. So first, let's recognize what is holding all of these nucleons, which are the particles inside the nucleus, protons and neutrons, in the nucleus. Because if protons are positive, shouldn't they be repelling? And they do. They do repel themselves. But what we need to recognize is that we have something called the nuclear force, or the strong force, that holds nucleons together, and it vastly overcomes any repulsion between protons. So neutrons are neutral. We don't have that attraction or repulsion, but there's still the strong force there for them as well. So all nucleons will have a strong force holding them together, and the strong force is very dependent on the distance between them. That if they're close together, we have a very strong force holding them together, but the further apart they are, the significantly weaker that force is. Okay. Now we notice something really interesting. We notice that if we take the mass of the individual nucleons, like 2 protons and 2 neutrons, and we add those masses together, that is a higher value than the nucleus that contains those exact same particles, that we've lost mass somewhere. And that was a really interesting, weird coincidence here. And so the difference between the mass of the individuals and of the nucleus was called a mass deficit. And so we were missing mass somewhere. And Einstein came and said that mass and energy are equivalent. And in order to combine all these nucleons, energy was released. It's a lot like fusion in stars. So energy was released, and that energy, through this equation, we saw equal the mass deficit. And so that mass was lost through energy of the combination of the nucleus. Okay. So, when we combine these nucleons, mass energy is released, okay, and this is through fusion. And we see that in stars mostly, and that's how we create these heavier elements. Really, stars, we have hydrogen, helium, and these really light elements, and then through nuclear fusion we can create heavier and heavier elements, and we release energy each time we do that. And it's quite a large amount of energy. And then on the other end, if these nuclei are so massive, then we can break them apart. Like uranium, you've probably heard that. We can break those apart, usually like with a free neutron, and that will release energy as well. This is called fission. This is what is done in nuclear reactors, atomic bombs, those kinds of things. That's how that energy is released. Okay. The energy needed to break apart a nucleus is called the binding energy, because that's what's holding it all together. So if we have a really high binding energy, then it is not easy to break that nucleus. We'd have to add a whole bunch of energy in order to actually break that. The higher the binding energy, typically the more stable the nucleus, and the lower the binding energy, the less stable. Okay. All right. Let's keep going. So that's kind of what we're seeing here. We have this binding energy versus mass number, and we see that higher binding gave us more stability. Oh, this kind of goes back to that strong force. So if we have 2 protons in the nucleus, they do repel each other because of electrostatic forces. In this case, it's like charges, so they repel each other. And so we have this repulsion, but there's still a strong force holding them together in the nucleus that is significantly larger than the repulsion. Now, neutrons are neutral, so they don't have an attraction or a repulsion as far as electrostatically, but in the nucleus, really close together, they have that strong force attraction. Same thing with a proton and a neutron. Even though this one's positive, the neutron's neutral, and so we don't have that attraction or repulsion, again, electrostatically, but we do have a strong force that'll hold them together in the nucleus. Okay. Now, you worked on an online lab where you created this band of stability, and we saw that we had this general trend, these darker elements here, and that those were our stable elements, and then above it we were less stable, and below it we were less stable. Okay? So what's an isotope? Let's address this, because we're going to talk about nuclear decay and isotopes being unstable. When two atoms are the same element, like uranium, that means they have the same number of protons. So if we look at the periodic table and we look at atomic number 92, that is uranium. Okay, uranium is always 92 protons. If we change the number of protons, we change which element that is. But we can change the number of electrons and keep the same number of protons. That would be an ion. But what we're focused on are isotopes, which is changing the number of neutrons. So we have the same number of protons, so they're both uranium, but we have different number of neutrons, and that's why these are isotopes of one another. If you add the number of protons plus the number of neutrons, that will give you the mass number. So hyphen number, that's your mass number, the number of protons plus the number of neutrons. Okay. All right, now, our band of stability. Let's keep talking about that. Okay. So here is, we're increasing our number of neutrons. Here we're increasing our number of protons. So we're changing each line up from here is a different element, right? And then we have this stability line here. Now, if we are staying in the same number of protons, but we keep increasing in neutrons, we get to a point where we don't have kind of enough neutrons, and then we find this stability point, and then we get to a point that we have too many neutrons. Okay, and how the element will decay to find stability is through a beta decay, and we'll define what that is here in a second. Now, you can argue that down here below, what our issue is we have too many protons, okay? That if we can reduce the number of protons, then we can find that stability. And so how that is done is through positron emissions. Okay, and we'll talk about that in a moment. And then we have this area up above. You can see we kind of end where we're stable, and then we just have these massive elements, just these high number of neutrons and proton elements. And in order to decay to something stable, we do this through an alpha decay. Okay. Now here's why it works. With beta decay, let's see, if I can put these next to each other. Okay, we'll come back to that diagram in a second. What happens in beta decay is that a neutron in the nucleus will actually alter and turn into a proton. And while it does this, we release an electron as well as an antineutrino. Okay? We're not going to get into details about neutrinos and antineutrinos. What I need you to be aware of is that for beta decay, it's an antineutrino. Okay? So we're going to take a neutron and we're going to make it a proton. So kind of looking back at this diagram here, we have too many neutrons. And so what we're going to do is we're going to lose a neutron and then add a proton, and you can see how that gets us closer to this band of stability. Right? So up above we tend to have beta decay to reach that band of stability. Okay. Now here's an example of this and what I want you to be mindful of. Mass number is up above, upper left, atomic number lower left. Okay, so carbon has an atomic number, which means the number of protons of 6. And we see that on our periodic table. We see atomic number 6, carbon. Right? And then we have a mass number of 14. Mass number is the number of protons plus the number of neutrons. Right? So we took carbon, which had 14, a mass number of 14. Okay, mass number 14, which is the number of protons, which we know is 6, plus the number of neutrons. So this is number of protons, this is mass number, and we'll have number of neutrons here. Now, in order to have a mass number of 14, and we know we have 6 protons, we would need 8 neutrons. Okay. Now, through beta decay, one of those neutrons is going to turn into a proton, right? So one of these neutrons will turn into a proton, so we won't have 8 neutrons, we will have 7 neutrons now. But then it turned into a proton, so then we'll have 7 protons. And again, mass number is the number of neutrons plus the number of protons, so our mass number didn't change. We just exchanged what nucleon the item was, going from a neutron to a proton. And that's what we see here, saying when carbon-14 decays through beta emission, that we have a nitrogen that's formed, which has a mass number of 14. That didn't change. And an atomic number of protons, of 7. And that's what makes it nitrogen. We go to our periodic table, we find atomic number 7. That's nitrogen. And then what is also emitted is beta decay. And beta decay is an electron and an antineutrino. It's beta emission. Okay. It's essentially just an electron because we're not going to worry or dive into our antineutrinos here. So we're basically taking a neutron, turning it into a proton, and through that process we're emitting an electron, and that's our beta decay. Okay. Now, conservation of mass also has to always be applied. So if we're starting with a mass number of 14, whatever we have on kind of this like reactant side or this parent isotope side, we have to see it on the daughter side as well as any kind of emission. Like what we start with, we have to end with. Mass is never created or destroyed, it's always conserved. So we'll see we have a mass number of 14 and then 14 plus 0, so we're still 14 on this side as well. And then we see mass is conserved as well below. It's just kind of this recognition that we had 6 protons, and then we had ended with 7 protons and an electron, which has that minus charge. And so this is almost recognition of charge more than anything. And so then we have 6 and then 7 minus the 1, so we have the 6. Okay, so what we have on top needs to be the same on the left and the right side of the arrows, and the same thing on the bottom. We have to have whatever we have on the left of the arrow also needs to be there on the right. If you can't see that or you don't have your notes printed, hopefully you do, it's a -1. Okay. When we have the next video, we'll talk about alpha decay and positron emission.